Okay, welcome everybody. Today we're going to be discussing a theorem of friends and strangers, which is also known as the party problem. Now, this theorem was first proven in 1928, and we're going to go and talk about what it's all about now. So, the theorem of friends and strangers asks the following question: Say that you have been invited to a dinner party. What is the smallest number of guests if you include the actual host themselves? You can be invited to a dinner party to guarantee that at least three people there are mutual friends, or at least three people there are mutual strangers. So, it's asking what's the minimum number of people to be at a dinner party to guarantee that at least three of them are mutual friends, or at least three of them are mutual strangers. And the way that this was solved was using something called graph theory. Now, graph theory is a branch of combinatorics, which involves the connections between different things. So graph theory uses vertices and it uses edges. So vertices and edges to connect things between them. Now, to solve this problem, we can think of people having connections between them. So, for example, um, the person who is a friend to another person. So, if you've got two people, we can represent the people as vertices, as dots, and the edges will connect between them. And what we do is we'll colour these edges differently. So a blue edge is going to indicate that two people are friends with each other, whereas a red edge is going to indicate that two people are strangers to one another. And in our problem, we're going to assume that you can either be a friend of someone or a stranger to that person. So you might have a work colleague, for example, that you are neither friends with and you also work with them. So you're more of an acquaintance. But in that case, we'll say that they're your friend. So we'll say that people that you know are your friends. Okay. And what we're looking for is these sorts of coloured triangles. So we're looking for a triangle of three people where each edge has the same colour. And we're saying what's the smallest number of people that you can gather together so that this is guaranteed to happen. Because, for example, if I only have three people in a gathering, two and three, so I've got my three people in a gathering. Well, person one and person two might be strangers to one another, and person two and person three might be strangers to one another as well. But that doesn't mean that person one and person three are also strangers. They could be friends. So we're asking the question, is there a number, what's the smallest number to guarantee that this either one of these two cases will happen at least once? Okay, so first of all, we need to ask ourselves, are there any numbers where we can guarantee we can color these edges so that this doesn't happen? So, for example, we know that this doesn't have to happen when we've got three people. We found a way of coloring these edges so that they're not all the same. So they're not all the same. What about with four people though? Is there a way of coloring the edges when it's four people? So let's say we've got four people in a gathering. And these four people, they're all going to be connected in some way. Now, this is a party of four guests. Each person can either be a friend of the adjacent person or they can be a stranger to the adjacent person. So there's always going to be an edge between each person. So each person is going to have a one, two, three edges. So they're going to have three edges going out from them. And so each edge is either going to be red or it's going to be blue. And our task is, can we colour these edges so there is no triangle which is either completely blue or completely red? And that triangle's got to encompass the same three people. So the way that we can do that is if I say that these two people are strangers and these two people at the top are also strangers and these people here are also strangers, And then I say that the rest of the people are friends. So friends, friends, and the last one as well. Then if I look at any three vertices on this graph, so let's look at this one. Well, this person, let's say this is person 2 here, then person 1 is a stranger, but person 4 is a friend. So this person's got um, no connections, so this person doesn't form a mutual triangle that's just completely red, completely blue. And that's the same for all of these vertices in this graph. Okay, what about for 5 vertices though? Is there a way of having 5 people? Is it guaranteed with 5 people that you'll be guaranteed a um, a group of 3 of them who are mutual friends or mutual strangers? So we'll try this with 5 as well. So 5 people. 1, 2, 3, 4, and 5. Okay. So each person is going to be connected in some way. And I'm going to propose that if these people are friends with each other on their outside, so make everyone a friend on the outside, and then we'll make everyone on the inside a stranger. Okay, now we haven't got 3 vertices of people who are all connected by um, the same color edge. So for example, if I label this person 1, this person 2, and this person 4, then person 1 and person 2 are friends. So person 1 and person 4 are strangers, and person 2 and person 4 are also strangers. Similarly, because of the way that I chose to colour the outside edges, all of these people are friends as well. But there's no blue triangle. There's no blue triangle. So for example, if I wanted to make a blue triangle, this edge here would need to be blue, but it's not, it's red. And similarly, if I wanted to make a red triangle, then one of these edges would need to be red, but none of these edges are red. So we've got a problem there as well. Okay, so 5 people does not guarantee that at least 3 of them will be mutually friends or mutually strangers. What about 6? Now, a bit of a spoiler alert, when we get to 6 people, um, we actually we actually can't stop it from happening. So 6 is actually going to be our answer, and I'm going to show why that's going to be true now. So let's suppose you have a graph on 6 vertices, and when we have these graphs where every single person is connected to that can be, so for example, earlier on we saw this graph here, we had 4 vertices, so 4 people, and there were these edges towards them like this. Oopsie. The graph where every single vertex is joined to another vertex, these graphs are called complete graphs. And the reason they're called complete graphs is because there's no more possible edges. So there's no more possible edges. Each vertex has already got an edge to another vertex, and so there's no more possible edges we can add to these types of graphs. So these are called complete graphs. And denoted Kn, where n is the number of vertices. So for example, this graph has 1, 2, 3, 4 vertices, so it's going to be K4. This one on the back has 1, 2, 3, 4, 5 vertices, so it's going to be K5. So that's a K4. This is a K5. Okay. So a K6 is going to be a graph with 6 vertices. And so we're going to be referencing K6s now, because we're going to say that for our theorem of friends and strangers, that you'll need the smallest number is going to be 6. So there's going to be 6 people that you need to have in this dinner party to guarantee that at least 3 of them are mutual friends, or at least 3 of them are mutual strangers. Okay, and how are we going to prove this? We're going to prove this the following way. We're going to um, select a random vertex in the graph, in the complete graph with 6 vertices. So we're going to call that vertex N. So we're going to let X be a vertex on the graph, on the complete graph on 6 vertices. And we got some notation for this. So this means let X belong to the vertex set on the complete graph of 6 vertices. So this notation is saying we're going to consider all of the vertices on the complete graph on 6 vertices, and we're going to look at some X. We're going to look at one of these vertices, and we're going to call that X. So, for example, when we looked at the complete graph of 5 vertices earlier, I labelled the vertices 1, 2, 3, 4, and 5. So I'm just picking one of these vertices arbitrarily. So let's say I pick this one arbitrarily, and I'm calling it X. So that's what I'm doing. I'm picking a random vertex on my complete graph on 6 vertices, and I'm labeling it X. Okay, so let X belong to the vertex set of the complete graph on 6 vertices. And I'm just going to label, so I'm going to draw a vertex, and I'm going to call it X. Now, how many vertices will this X be connected to? So if I was to draw edges, how many edges should I draw? Well, when I had my complete graph of 5 vertices, if I look at my vertex here, you can see that there's 1, 2, 3, 4. So it's got 4 connections. It's connected to 4 different vertices. The complete graph of 4 vertices is connected to 1, 2, 3. So for a complete graph of 6 vertices, there's going to be 1, 2, 3, 4, and 5 connections. There's going to be 5 edges coming from this vertex. Okay, that's the first thing. Now, with these edges, we need to colour them as well. So we need to colour these edges as well. And I'm going to do so in the following way. So let's look at our X again. And it's got our 5 edges, but they need to be coloured in a certain way. Now, let's say 3 of them are red, then the rest of them must be blue, of course. So the rest of them must be blue, like this. And similarly, if 3 were blue, then only 2 could be red. But we are guaranteed something. We are guaranteed that at least 3 of them will be red, or at least 3 of them will be blue. So we're guaranteed that. We're guaranteed that at least 3 of these edges will be red, or at least 3 of them will be blue. And to demonstrate that, if I were to pick my vertex X, and let's say only one of these edges was blue, let's say just the one edge was blue, well, we know that this vertex X has got to have another 4 edges coming out of it. So these remaining 4 edges must all be red. 1, 2, 3, and 4, like that. And you can do a similar game with 2 red edges, 4 blue edges, etc. So you're guaranteed that at least 3 of the edges are going to be red, or at least 3 of the edges are going to be blue. So I'm just going to say, for sake of argument, let's say that those 3 edges are red. We'll say that there are 3 red edges. So we've got at least 3 red edges. That's guaranteed. Okay. And I'm going to call these vertices that are connected by this edge to x, I want to call them y1, y2, and y3. So they're going to be edges. So these vertices are going to be y1, y2, and y3. Now, here's an observation. If y1, if this edge here between y3 and y2 is red, then we have our red triangle guaranteed already. And similarly, if this edge here is red, then we are also guaranteed our triangle here as well. So in this case, x, y3, and y2 form a triangle. And in this case, x, y2, and y1 form a red triangle. And in that case, we'd be guaranteed that we'd have the three mutual strangers. So if all of these edges are red, and these edges are red as well, then we've got our three strangers. So instead, we're going to assume the opposite, or the contrary. So we're going to assume that we've got our x here, and we've got our three red edges. 1, 2, and 3. And we've got our endpoints. And we've labelled them y1, y2, and y3. Okay. Now, again, if any of these edges are red, we've got our red triangle. So the only alternative for having one of these edges to be red is if all of them are blue. So if all of these edges are blue, so we've got this edge here is blue, and this edge here is also blue. And this last edge is also blue. But what's the problem? Now we've got all our three edges of blue instead of red. But what's the problem with that? Well, it means that y1, y2, and y3 form a blue triangle. That's a problem. Why is that a problem? Because that means that we have three mutual friends. So if you invite 6 people to a dinner party, you are guaranteed to have 3 mutual friends, or at least 3 mutual strangers. So at least 3 mutual friends, or at least 3 mutual strangers. And it's the smallest number possible to guarantee this, because if you go any smaller, you can find a different way to colour the edges between these vertices. And that is the theorem of friends and strangers. So that's our solution to the theorem of friends and strangers. And this is basically the so-called folklore theorem, which inspires the branch of mathematics called Ramsey Theory. And this problem was first solved by a mathematician called Frank Ramsey. He solved it in 1928, and his paper was actually published 2 years after he died. So he died in 1928, in the same year that he solved the problem, and then his paper was actually published in 1930. The way that Ramsey did it, though, was he didn't actually prove it using graphs and edges of graphs. He used it in a very much accounting way. However, so considering those combinations, basically. However, the modern day Ramsey theory is all about using these graphs and these colorings to think of properties of numbers, which is what we're going to be studying going forward. So yeah, hope you enjoyed. Share your thoughts in the comments below.